January 1965, deep in the remote expanse of the Kazakh steppe, a special military truck carefully made its way over the rugged terrain, carrying a cargo unlike any other. Inside lay a nuclear device, an imposing explosive nearly 3 feet in diameter and 10 feet tall, bristling with destructive power. This was no ordinary test. For months, Soviet scientists and military officials had been meticulously preparing for this moment, watching the weather closely, waiting for the perfect conditions to proceed. Finally, the weatherman's forecast cleared the path, and the mission was greenlit. The truck came to a cautious stop, and a team of technicians began the delicate process of unloading the nuclear charge. Slowly and carefully, the bomb was lifted and lowered into a pre-drilled shaft that plunged 584 feet beneath the Earth's surface. Despite the depth, the bomb reached the bottom, secured in its subterranean chamber. Hours passed as final preparations were made, and then the countdown began, one that would mark a singular moment in nuclear history. Time seemed to crawl as anticipation built. At last, only 5 seconds remained. Then, the charge detonated. The resulting explosion released a yield estimated at 170 kilotons, about 8 times more powerful than the atomic bomb dropped on Hiroshima 2 decades earlier in August 1945. The deafening roar echoed across the barren steppe. Within just a few seconds, a blazing cloud of superheated gas began to rise, expanding rapidly. 5 minutes after detonation, this column of scorching gas soared to nearly 16,000 feet. The force of the blast was staggering. Approximately 10.3 million tons of soil were hurled skyward, reaching heights of over 3,100 feet before settling back to Earth as fine dust. This tremendous upheaval carved out a vast crater, measuring 410 feet across and plunging 328 feet deep, a newly formed scar etched onto the landscape. Despite its sheer scale, the story of this explosion and the strange lake it created remains little known. Fewer still understand why the Soviet Union embarked on such a project in the first place. To unravel this mystery, we need to step back and understand the context behind this extraordinary experiment. The event, known as Project Chagan, took place at the Semipalatinsk nuclear test site in what is now Kazakhstan. This location had been chosen carefully. It was remote, desolate, and far from population centers. The Semipalatinsk site had long served as the Soviet Union's primary proving ground for nuclear weapons, located roughly 80 miles from the nearest town, Semey. Unlike earlier weapons tests designed purely for military purposes, Project Chagan was part of a broader Soviet initiative called Nuclear Explosions for the National Economy. This program aimed to explore peaceful, industrial, and economic applications of nuclear detonations. The idea was to harness the immense power of nuclear explosions for constructive purposes, such as mining, reservoir creation, and even stimulating oil production. To minimize risks, the scientists involved had to meet stringent requirements, chief among them ensuring that radioactive fallout released into the environment would be minimal. The test site chosen was the dry riverbed of the Chagan River, a seasonal watercourse they intended to partially divert, hoping the explosion would create a crater that could be flooded to form a new reservoir. The project leader, Ivan Turin, later recalled the haunting beauty of the blast. "I've never seen such a beautiful sight from a nuclear blast before, even though I'd witnessed plenty of air bursts." Such a sentiment might seem surreal today, but in the 1960s, the awe inspired by nuclear explosions was often mixed with a sense of scientific optimism. About 50 days after the detonation, once the dust and radioactivity had sufficiently settled, work began in earnest to connect the newly formed crater with the nearby river. Time was pressing, spring was approaching, and the seasonal floodwaters needed to be channeled quickly. Using heavy machinery and conventional explosives, crews dug a canal to link the crater to the Chagan River. Estimates of how many people worked on this vary. Some say around 180, others as many as 300, but all agree that the effort was intense and urgent. When the canal was ready, workers detonated a barrier separating the river and the crater, unleashing a torrent of water that flowed at a staggering rate of over 500,000 gallons per minute. The crater filled rapidly, exceeding expectations. Within 3 days, it held nearly 800 million gallons of water, swelling to 2 billion gallons shortly thereafter. Nearby, a separate reservoir formed, holding an additional 3 billion gallons. So, why go through all this trouble? The goal was practical: to develop methods for creating water reservoirs quickly and efficiently in Central Asia's arid climate. The region suffered from severe water shortages, with rivers drying up each summer. The concept was that nuclear explosions could carve out natural basins, perfect for collecting and storing precious spring runoff. These reservoirs could support irrigation, provide water for livestock, and even serve as community water sources, reducing evaporation by concentrating water in deeper basins. Soviet planners envisioned dozens of such reservoirs across Kazakhstan alone, around 40 artificial lakes, with a combined capacity of up to 37 billion gallons. The idea seemed like a promising fusion of cutting-edge science and environmental engineering. Yet the scientists underestimated a critical factor: radiation. Back then, the concept of peaceful nuclear explosions was embraced with optimism, embodied in slogans like "the peaceful atom in every home." After the Soviet Union tested its first atomic bomb in 1949 and broke the U.S. monopoly on nuclear weapons, attention turned toward harnessing atomic power for non-military purposes. Stalin's 1950 decree had set the stage for exploring nuclear energy beyond weapons, including electricity generation and large-scale engineering projects. This decree also initiated what would become the world's first nuclear power plant at Obninsk. But equally important were the plans to use nuclear detonations for large-scale excavation and resource development. Out of this grew the nuclear explosions for the National Economy Program, under which Project Chagan was conducted, one of 124 peaceful nuclear explosions the USSR carried out between 1971 and 1988. Returning to the lake, Soviet propaganda films at the time claimed that by 50 days post-explosion, radiation levels were safe, with soil and water samples reportedly showing no threat to humans. Newspapers like Izvestia described Chagan Lake as a pristine body of crystal-clear water, transformed from barren steppe into a vibrant reservoir. The belief in safety extended even to people. In a symbolic gesture, the Minister of Machine Engineering, Efim Slavsky, nearly 70 years old, swam in the lake. Remarkably, Slavsky lived to 93 without apparent health issues, which Soviet officials touted as proof of the lake's harmlessness. But what about wildlife? Scientists introduced a bewildering assortment of flora and fauna into the lake to test its habitability. They stocked it with 36 fish species, including piranhas imported all the way from the Amazon. They also released mollusks, amphibians, reptiles, mammals, invertebrates, and nearly 150 species of aquatic plants, supported by a biological research station set up on site. The results were disastrous. Most species failed to thrive. While some fish survived temporarily, successive generations exhibited alarming mutations, deviating drastically from their original forms. Over time, around 90% of introduced species perished, with only carp managing a limited foothold. These findings shocked scientists and ultimately led to the project's cancellation. By 1974, workers at the site were withdrawn, and the true consequences became undeniable. The massive fallout from the blast had contaminated the lake's surroundings so severely that even decades later, it remains one of the most radioactive areas on the Semipalatinsk test site. Health impacts on personnel who worked directly at the site were severe. Many died prematurely despite beginning the project as young, healthy individuals. The broader local population suffered as well, though comprehensive studies on health effects only began years later, and data remains incomplete. What is known as chilling, radioactive isotopes like plutonium-239, with a half-life of 240,000 years, were detected in the vicinity, signaling contamination that will linger for millennia. The initial vision, to create life-giving water reservoirs, backfired. While the crater did fill with water during the spring thaw, the lake's edges dried out each summer. Local communities avoided the site, wary of invisible radiation dangers, and disturbed by the lifeless, black surface of the water, surrounded by bleak mounds of earth. The Chagan River eventually altered its course to bypass the crater entirely. The explosion also caused geological transformations. Intense heat turned local mountain rocks into glass-like formations, a testament to the power unleashed underground. Radioactive dust from the blast spread far and wide, carried high into the atmosphere. Fallout reached 11 settlements, totaling about 2,000 people, many exposed to dangerous radiation doses exceeding safe thresholds. Those most exposed, naturally, were the workers and scientists at the blast zone, numbering perhaps 300, though secrecy shrouds exact figures. Despite the controversy and tragedy, peaceful nuclear explosions continued across the USSR, 124 in total, conducted for purposes ranging from oil extraction to mining and seismic research. Similar programs ran in the United States, with 27 peaceful explosions carried out between 1957 and 1973, though often with less regard for radioactive contamination. For instance, near Lake Miu in Bashkortostan, nuclear blasts nearly doubled oil extraction efficiency, demonstrating some practical success. Still, the human and environmental costs cast a long shadow. Today, the remnants of Project Chagan linger as a stark reminder of Cold War-era hubris and the risks of tampering with nature through nuclear force. The lake, still radioactive, serves as a ghostly testament to a time when science, politics, and ambition converged in a dangerous experiment, one that created an atomic lake neither peaceful nor sustainable. The Gobi Desert is one of the harshest environments on Earth, barren, dry, and seemingly lifeless. But far from being ignored, it has become a proving ground for some of China's most ambitious projects. From large-scale greening efforts to advanced technological developments, the desert is being transformed. Vast stretches of sand have already been turned into thriving, oasis-like zones through aggressive anti-desertification campaigns. Trees and vegetation are being planted across wide swaths of land, turning the seemingly impossible into reality. These greening experiments are part of China's broader environmental efforts, aimed at reclaiming land and fighting climate change. But amid these environmental transformations, there's another side to the story, one that involves cutting-edge science, nuclear technology, and an underground megastructure. At first glance, some parts of the Gobi still appear untouched, just sand, wind, and sparse vegetation. But hidden beneath one of these unassuming areas lies something much more complex. Recently, a massive underground facility began to take shape. The first signs were subtle, some construction activity, a few new buildings. But what's buried below the surface is far more significant. Chinese engineers have dug a tunnel more than 919 feet into the ground. And that's just the beginning. This tunnel is merely the initial phase of a sprawling complex that, once complete, will include over 8 miles of subterranean passages. So, what exactly is China building beneath the desert sands? To understand the bigger picture, we need to rewind a bit and look at China's nuclear journey. China's nuclear energy program began in the 20th century, and by 2002, the country already had 5 nuclear power plants and 7 operating reactors. Their combined capacity was modest, only about 4.5 gigawatts. But just like the rest of the country, China's nuclear industry was poised for rapid expansion. By 2005, reactors that had been under construction since the 1990s finally came online, boosting capacity to 15 gigawatts. In 2014, that number increased to 19 gigawatts. The pace might seem slow at first, but that growth marked the beginning of a new era. From there, the expansion accelerated dramatically. By 2023, China's nuclear capacity had jumped to 53.2 gigawatts, nearly tripling in less than a decade. For comparison, the United States, China's main competitor in this field, took nearly 40 years to accomplish a similar scale of growth. But China isn't stopping there. In the early 2020s, the Chinese government unveiled a staggering plan: the construction of 150 new nuclear reactors over just 15 years. If successful, this initiative would bring China's total nuclear capacity to 200 gigawatts by 2035. The scale of this effort is unprecedented. It's expected to cost between $370 billion and $440 billion, but in a country known for its megaprojects, that level of investment is not unusual. With this level of output, China could provide power to dozens of major cities, each the size of Beijing, and drastically reduce its reliance on fossil fuels. But there's a bigger goal in sight. By 2050, China wants 15% of its electricity to come from nuclear energy. Why nuclear? Because it's far more efficient than alternatives like solar or wind, although China has also heavily invested in both of those. More importantly, nuclear power offers a path away from coal, the dirtiest and most polluting of all fossil fuels. Coal still dominates China's energy mix, and moving away from it is critical to reducing the country's massive carbon footprint. If China hits its nuclear targets, it could slash its annual carbon emissions by 1.5 billion tons, more than the total emissions of the UK, France, Germany, and Spain combined. That gives a sense of both the challenge China faces and the size of its potential contribution to the global climate effort. To support this ambitious transformation, China has developed what's called the Plan for 60, a vision to eventually replace all 2,990 of its coal-fired power plants with cleaner nuclear alternatives. However, like all technologies, nuclear power comes with its own set of problems. Chief among them, nuclear waste. Most of the waste generated by nuclear plants, about 99%, is classified as low or intermediate level waste. This includes things like contaminated tools, clothing, filters, and metal parts. These materials are relatively easier to handle. They're sealed in protective containers and buried at depths of up to 330 feet in designated storage facilities. China already has several such facilities in operation. But then there's the remaining 1%, the truly dangerous stuff, high-level radioactive waste, HLW. This mainly consists of spent nuclear fuel, and it can remain dangerously radioactive for tens of thousands to hundreds of thousands of years. Disposing of HLW safely is one of the biggest challenges in the nuclear industry. The international consensus is that it must be buried deep underground in stable geological formations at depths of at least 1,640 to 3,280 feet. The goal is to isolate the material for thousands of years, ensuring it won't harm future generations. China didn't wait until its reactors were fully online to start planning. As far back as the 1980s, the country began looking for the perfect disposal site. After years of research and testing, experts found that Inner Mongolia and parts of the Gobi Desert had some of the most promising geology. Since the 1990s, Nearly 100 deep wells have been drilled in these areas to take core samples, altogether totaling about 37 miles of extracted rock. These studies revealed the presence of stable granite formations, ideal for underground storage. In 2021, near the city of Zhuquan in Gansu province, China officially broke ground on its most ambitious nuclear waste project yet, the Beishan Underground Research Laboratory. To dig the tunnels, China deployed a monster machine called Beishan 1, a 330-foot-long, 23-foot diameter tunnel boring machine designed specifically for steep rock formations. It's the world's first machine of its kind. In just a few years, it has already carved out an entry ramp more than 918 feet deep. But this is only the beginning. The finished lab will be enormous, more than 18 million cubic feet of underground space, including 8 miles of tunnel and 3 vertical shafts. On the surface, the site will span 610 acres, complete with administrative buildings and other facilities to support long-term operations. Construction isn't expected to be finished until 2038, but even then, China doesn't plan to immediately store its HLW there. Instead, a long period of scientific study and observation will follow. Researchers will monitor the site until 2050 to ensure that the geology is suitable for long-term storage. Only after confirming its safety, perhaps 3 decades from now, will China begin to store its most dangerous radioactive waste there. Still, this doesn't mean the project will go to waste if something goes wrong. Even if Beishan is ultimately deemed unsuitable for storage, it will still serve as the world's largest underground laboratory for studying HLW disposal. It's already a global hub for nuclear waste research. China has shared data and collaborated with over 10 countries and regions, as well as with the International Atomic Energy Agency, IAEA. More than 100 international experts have visited the facility. In 2024, the site even hosted an IAEA training event focused on the design and construction of underground disposal systems, with participants from 17 countries, including France, Sweden, and South Korea. As one Chinese official put it, this underground lab doesn't just belong to China, it belongs to the world. The knowledge gained at Beishan could help other countries develop safe nuclear waste storage solutions, too. And if Beishan proves successful, China will have laid the groundwork for one of the safest HLW disposal systems ever built. But China's nuclear ambitions don't stop at fission. There's another frontier it's exploring: nuclear fusion. If fission is the engine of today's nuclear power, fusion is the dream of tomorrow. You might have heard headlines about China's artificial sun. That's a nickname for the experimental advanced superconducting tokamak, or EAST. It's one of the world's most advanced nuclear fusion experiments. EAST creates plasma at temperatures exceeding 150 million degrees Fahrenheit, hotter than the core of the real sun. Magnetic fields keep the superheated gas suspended, preventing it from touching the reactor walls. The goal: controlled nuclear fusion, the process that powers stars. If successful, fusion could generate 4 times more energy than traditional fission without producing long-lived radioactive waste. It's fueled by deuterium and tritium, which are far more abundant than uranium. Deuterium is found in seawater, and tritium can be manufactured. And because fusion produces much less waste, and that waste decays quickly, it could solve the biggest problem facing today's nuclear power systems. For now, fusion remains experimental, but with projects like EAST, China is putting itself at the forefront of the race to develop the next generation of clean, limitless energy. So while the Gobi Desert may seem empty, it's actually one of the most important testing grounds in the world for technology, for science, and for humanity's energy future. Vast stretches of golden sand slowly turning green, millions of trees planted on barren ground, hundreds of square miles of once lifeless desert transformed into fertile land where farming and life itself can thrive again. This isn't science fiction. It's a real-life environmental revolution led by China, a country that has taken the challenge of turning the uninhabitable into the livable to a whole new level. With the collective effort of local communities, experts, and national authorities, China is reversing decades of damage done to its arid landscapes. And although desertification remains a significant threat, China's large-scale greening projects have shown that even the harshest terrains can be reclaimed. One of the most ambitious of these efforts is centered in the Muas Desert. Here, Chinese citizens planted thousands of saplings directly into the sand, often with little or no water. The idea sounded impossible. So what happened next? Let's find out. Northern China, specifically the Ordos Plateau in the Inner Mongolia Autonomous Region, was once a lush area filled with rivers, lakes, and dense vegetation. It was home to thriving ecosystems and vibrant biodiversity. But over time, human activity took a heavy toll. Deforestation, overgrazing by livestock, and unsustainable farming practices slowly chipped away at the land's fertility. What remained was a vast, expanding desert. By the mid-20th century, the Muas Desert had swallowed up over 16,000 square miles of land, Fertile soil was replaced by shifting dunes and rocky plains. Once productive farmlands turned to dust. The desert became not just a symbol of environmental degradation, but a daily struggle for survival. Take the city of Ulan, for example, located right on the desert's edge. Over the decades, sandstorms repeatedly buried homes, farmland, and roads. The winds were so powerful and frequent that Ulan had to be relocated not once, but 3 times. Harsh winters added another layer of difficulty, with freezing temperatures transforming the desert into a deadly, icy wasteland. Locals would often wake up to find thick layers of sand piled against their doors. Digging out was a daily routine. Abandoned homes, left unprotected, were quickly consumed by the dunes, their roofs and walls slowly disappearing beneath the sand. And all the while, the desert kept growing. Records from Ulan show that in the 100 years leading up to 1949, about 540 square miles of fertile land were overtaken by sand. 6 county-level towns and over 400 villages and settlements were either damaged or lost entirely. By that time, forest and grassland coverage in the region had plummeted to just 1.8%. People considered leaving. But for most, there was nowhere to go. The 1950s and 60s were a time of extreme hardship for China. Following the rise of the People's Republic, the nation underwent a radical transformation, socially, economically, and environmentally. During the Great Leap Forward, traditional farming systems were upended in favor of large-scale collective agriculture, but the methods used were often untested and inefficient. One of the more infamous examples was the Four Pests campaign, a well-intentioned but ultimately disastrous attempt to eliminate rats, flies, mosquitoes, and sparrows. With sparrows nearly wiped out, locust populations exploded, decimating crops and triggering one of the worst famines in human history. By 1959, over 600 million people were living in poverty. That year's harvest was 15% lower than in 1958, and by 1960, agricultural output had dropped to just 70% of what it had been 2 years prior. In purely numeric terms, China's agricultural production fell from 200 million tons in 1958 to only 143.5 million tons by 1960. This crisis only worsened the situation in desert regions like Muas. Starvation forced people to make hard choices: stay and fight the land, or perish. So they fought, but not with weapons, with trees. In the 1950s and 60s, a grassroots movement began to take shape. Locals, determined to reclaim their land, started planting trees by hand. Millions of them. Some even sold their livestock to buy saplings, understanding that the animals wouldn't survive without vegetation anyway. One farmer famously sold 84 sheep to buy enough saplings to create a 3.7-mile-long green belt along the southern edge of the Muas Desert. He wasn't alone. Entire families dedicated decades of their lives to planting and nurturing trees. In some cases, 3 generations worked on the same plot of land, slowly turning sand into soil. As the trees took root, they began to change the landscape. Their roots helped stabilize the sand, brought water closer to the surface, and created shade, conditions that encouraged smaller plants and grasses to grow. With every new tree, the next batch had a better chance of survival. The Chinese government supported these efforts. Scientists were brought in to study desertification and recommend solutions. Water-retaining grasses and drought-resistant trees were introduced, and over time, the once unstoppable dunes began to slow. But one major problem remained: moisture, or rather, the lack of it. Most deserts, including Muas, suffer from extremely low rainfall and high evaporation rates. As a result, many planted saplings withered and died, despite the best efforts of locals. That changed in 2004, when a desertification expert proposed a groundbreaking solution. His team introduced a soil hydrodynamic treatment method, essentially preparing the soil in a way that retains moisture and reduces evaporation. The process helps balance the needs of young plants with the water-holding potential of the soil. The result? Survival rates soared. Suddenly, it became possible to plant trees in dry desert soil, without irrigation, and still have them thrive. So what has all this hard work led to? The results are nothing short of miraculous. One powerful photo comparison tells the story best. In 1998, a young boy and his grandfather planted a poplar tree in the Muas Desert. By 2020, both the tree and the boy, now a man, had grown tall. Behind them, what was once a desolate landscape had become a green oasis. Since the beginning of the campaign, over 40 million trees have been planted in the Muas Desert. Species like Glanz larch, a hardy evergreen introduced decades ago, are now thriving thanks to these new techniques. Today, Glan's Larch covers more than 330 square miles of the desert. And Larch is just the beginning. In nearby Yanwan, on the edge of the Muas Desert, the AI Lavender Ecological Base has become a colorful paradise. Covering over 4,900 acres, the area now blooms with more than 3,000 acres of lavender, plus hundreds of acres of other flowers like verbena and chrysanthemums. Ulan, once a symbol of desertification, now stands as a model of recovery. Forest coverage in the city rose from less than 2% in the 1950s to 33% by 2020. Every year, locals continue to plant thousands more saplings. In 2020 alone, their target was to reforest nearly 1,000 acres of desert. The government and private companies have also joined the fight. In the first quarter of 2020, 41 entities, both public and private, planted trees on more than 82,000 acres of land near Ulan. But what about the bigger picture? Well, the results are even more astonishing. In the 20th century, the Muas Desert stretched across 16,300 square miles. Today, over 93% of that land has been reclaimed, now covered with greenery, thriving ecosystems, and agricultural potential. Once a barren stretch of wasteland, the Muas Desert is rapidly becoming a symbol of resilience, restoration, and hope. While challenges still remain, especially with ongoing climate change, the progress made so far proves that with determination, science, and community effort, even the harshest environments can be brought back to life. So, can deserts be stopped? In China's case, the answer is already growing. In 2021, news outlets started buzzing once again with something new. China was building yet another mysterious structure in the middle of the Gobi Desert. At first glance, it didn't raise too many eyebrows. After all, China is no stranger to grand-scale construction projects in the middle of nowhere. But this time, it wasn't a solar farm or a military testing site. It turned out to be a nuclear power facility. Still not surprising? Fair enough. China already has dozens of nuclear plants scattered across the country. But dig a little deeper, and things start to get a lot more interesting. Because this wasn't just any nuclear reactor. This one was powered by a rather obscure element, thorium. And the more you learn about it, the more it starts to feel like something out of a science fiction novel. Back in 1828, the Swedish chemist Jöns Jacob Berzelius discovered a new element and gave it a name that sounded straight out of Norse mythology. He called it thorium, after Thor, the god of thunder. On the periodic table, thorium sits with the actinides and carries the atomic number 90. It's a silvery metal, slightly radioactive, and it turns out, it might just hold the key to revolutionizing nuclear energy. Now, if the word radioactive makes you uneasy, don't worry. Thorium is radioactive, but only mildly. That's because all naturally occurring thorium is thorium-232, an isotope with a half-life so long it stretches the imagination. To put it in perspective, thorium-232 has been around since before the Earth was even formed. Some scientists believe it predates the solar system itself, possibly even going back to the aftermath of the Big Bang. And billions of years later, it's still decaying, very slowly, because of its low-level radiation. Thorium is surprisingly safe to be around in small concentrations. In fact, it's found in beach sand all around the world. One of the most common minerals containing thorium is called monazite. This mineral can contain anywhere from 3.5% to 10% thorium by weight. That might not sound like a lot, but when you consider the sheer volume of monazite-rich sand in certain parts of the world, it adds up. So, how much thorium do we actually have access to? Well, thorium is far more common than you might think. In the Earth's crust, it's found an average of 10.5 parts per million. For comparison, tin, a metal we use all the time, is present at only 2.3 parts per million. Even gold, that famously precious metal, only appears at about 1.8 parts per million. Thorium is, relatively speaking, everywhere. When it comes to national reserves, India holds the top spot. The country has about 340,000 tons of thorium, most of it in its western coastal regions, where monazite sands are abundant. China isn't far behind, with roughly 280,000 tons of industrial reserves. But there's an important difference. India's thorium is mainly found in beach sands, while China's thorium is buried deeper and not mined directly. So how is China getting its hands on so much thorium? Here's the clever part. China doesn't need to mine thorium directly. That's because thorium is a byproduct of rare earth mining, and in the world of rare earth elements, China is the undisputed heavyweight champion. As of 2023, China produced 70% of the world's rare earth elements and processed about 90% of them. These materials are essential for making everything from smartphones and electric vehicles to wind turbines and guided missiles. And the epicenter of this production is a massive operation in Inner Mongolia, the Bayanobo mine, located about 93 miles northwest of Baotou, spread over 19 square miles. It holds a majority of China's rare earth reserves, and one of its key minerals is, once again, monazite. After extracting the rare earth elements from monazite, what's left behind is usually discarded as waste. But that so-called waste contains significant quantities of thorium. So, thanks to its booming rare earth industry, China ends up with a steady, almost effortless supply of thorium. This gives the country a serious strategic advantage. Thorium has a variety of uses. It's added to metal alloys like magnesium and aluminum to improve their strength and heat resistance. It's also used in welding electrodes and even in high-end optical lenses, where it helps increase light refraction. These applications are helpful, but they pale in comparison to thorium's most promising use, nuclear power. The idea of using thorium as nuclear fuel isn't new. Back in the 1960s, American scientists at the Oak Ridge National Laboratory in Tennessee experimented with a completely different kind of nuclear reactor, one that didn't rely on uranium or plutonium. Led by nuclear pioneer Alvin Weinberg, researchers developed a reactor that ran on uranium-233, which isn't found naturally but can be produced by irradiating thorium-232 with neutrons. Over time, thorium-232 absorbs a neutron, undergoes a few decay steps, and becomes uranium-233, a fissile material capable of sustaining a nuclear chain reaction. Between 1965 and 1969, Oak Ridge ran an experimental molten salt reactor for a total of 15,000 hours. It used a mixture of fluoride salts with thorium dissolved into the solution, producing nearly 8 megawatts of thermal power. It was a major technological breakthrough, but the world wasn't ready. The materials needed to handle the high temperatures and corrosive nature of the molten salt weren't available at the time. Additionally, the U.S. nuclear industry had already committed to uranium-based solid fuel reactors, which were better understood and aligned more closely with military needs. The thorium reactor was shelved and largely forgotten, until now. Fast forward to 2021. Deep in the Gobi Desert, about 75 miles from the city of Wuwei, China successfully built and tested a new molten salt thorium reactor. For the first time since Oak Ridge, a thorium-powered system achieved stable nuclear fission. The Chinese reactor isn't huge. Its thermal output is just 2 megawatts, and it doesn't yet generate electricity. But that's about to change. China plans to scale up and build a new reactor with a thermal capacity of 60 megawatts and an electrical output of 10 megawatts. These are still small by commercial standards, but they mark a significant milestone. You might be asking, why go through all this trouble? Why not just stick with tried and true uranium reactors? There are several compelling reasons. First, China is concerned about long-term uranium supply. The country has over 50 nuclear power plants that together generate roughly 400 terawatt-hours of electricity per year. That accounts for about 5% of China's total energy production, which, given China's massive demand, is a substantial chunk. And it's only the beginning. Between 2005 and 2020, China added about 3.4 gigawatts of nuclear capacity annually. From 2020 onward, they've increased that goal to 9 gigawatts per year. Clearly, the country is betting big on nuclear, and that means finding alternative fuels is crucial. Thorium is 3 times more abundant than uranium. According to some estimates, China's thorium reserves alone could power the nation for up to 20,000 years. That kind of energy security is hard to ignore. And there's more. China, like much of the world, is pushing toward zero emissions. The country is investing heavily in solar, wind, and hydropower, but these sources have limitations. Nuclear energy, on the other hand, is dense, reliable, and carbon-free. While traditional uranium reactors have long raised concerns about safety and nuclear waste, thorium-based systems offer promising solutions. For one, they produce far less long-lived radioactive waste. The molten salt design is also considered inherently safer. If the reactor overheats, the fuel can drain into a containment vessel and cool off naturally, avoiding meltdowns. So, what China is doing in the Gobi Desert isn't just another mega project. It's a potential leap forward in how humanity generates clean, abundant energy. With the world facing increasing pressure to decarbonize and reduce its reliance on fossil fuels, thorium might just be the underdog we've been waiting for. And if that's the case, we'll be seeing a lot more quiet revolutions beginning in the desert.